to talk about abstract algebra for analytics. So before we dive into that, let me give first a context on how this thing, on bringing this abstract algebra, which is a mathematical domain that's not very much used today, bring it into building analytical systems. So it started out actually on Twitter. So you had Steve Noble, who is one of the lead data scientists at Stripe, tweeted one day, if you're building, I'm sorry, my phone is ringing, I'm going to turn it off. Please stop tweeting now.
Chaque fois qu'il fait un truc comme ça, je vais chanter.
Okay, so Steve Noble tweeted out, if you're building a system for calculating aggregates and you don't know the relevance of things like abelian group, then stop, okay? So I know Steve, so I was like, okay, dude, what you talking about? I mean, come on. I do these kind of things, and I forgot what abelian groups are. Then discussions ensued on Twitter, and afterwards I started thinking, what exactly we're trying to do? My job, and I assume many of you here, since you heard it already this morning, is that what you're trying to do is build analytical and scalable systems. Most of them are distributed, and you realize at the end that most of the analytical systems that you're building amount to counting and adding in any way. I mean, what you're doing in machine learning at the end of the day is actually doing multiplications, additions, all the time. And once you've realized that most of the thing that you do is addition and multiplication, you start thinking, okay, why not? What kind of operation do we have? How can we use this abstract algebra, which is built around addition and multiplication and all the properties to build analytical systems? So before I go into explaining what abstract algebra is, let's go first within an example. This is a practical one. Let's say you have something like a set of records, whether it's streaming or you have it in a huge data set. What you're trying to do is to find the top k element. Top k element is actually finding the top or the k first element in a certain order in a certain data set. So what you usually do, which is quite easy, you have an input, you read it, you put it into something, your program, you do a source, you filter them, and you take the top k records, and then you write your output. So here you have 11, 12, and all the examples below. You want to find the top 3 elements of this sequence. What you do is actually do the same thing, and at the end of the day, you have something like 56, 48, 12, which is quite easy, which is simple in some way. Now, since we work in big data, and in big data, Hadoop and MapReduce is still king, may he die soon, I might say. What you have actually, the workflow in MapReduce is something like this. You have HDFS with its blocks, and you have each input you have all the steps. You have the mapper, and you have the reducer, all of it. So when you take something like a top k element, this is what you have. You have multiple data sets. You do a mapper, you do all the storing, all the combining in the middle, and then you shuffle it into the reducers. But in reality here, a lot of things happen. You're not just taking mapper and pushing them into reducers. In the middle, you have things called combiner, which are some kind of reducer, but some kind of reducers happening on the map side, not just on the reducer side. And you also have some sorting, some filtering, but all of that is happening on the map side. So before you go straight into reducer, most of the time what you want to do is actually leverage what you have behind into the map side. But this sometimes, in most operations that you have, is quite costly because many of the frameworks, libraries that we have usually do MapReduce by, like Hive, for example. It creates a lot of jobs and append them do a workflow of multiple jobs, and that's costly. I use something called scalding. Scalding is a Scala DSL, which is more not just a DSL, but actually a huge framework with a lot of optimization to write Hadoop jobs. And if I want to do something like take 2 collections and find the top k of the 2 collections, this is what it looks like. And you get something like this in the middle, actually. You filter, you do a join of your 2 collections, you filter out, and you group by. Or I think the next group by should be highlighted as well, but yes, this is what happened on Red Slide at 3 a.m. Here, what you have is actually you do a join, you filter out, and you do a group by. But like I said, this operation here, if you rotate it to something like pig or of many things, what you have multiple jobs, or you have a lot of performance issues. Why? Because like what we had in my first figure, what you have is the cost of the last reducer. When you're appending multiple jobs, sometimes the last job is the slower one. So what you want to do is to avoid to be stuck by a job waiting for the first jobs to finish. And if I come back here, you see that you have a lot of chatter here because you have mappers talking to all the reducer. The network can be very, 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 very heavy. So you want to avoid to send all your data in the network at the same time. So what you want to do is actually use it in a very efficient way to send something to pipeline all your data and do it in a single pass. And here, the order of the map and the reduce of the reducers are very expensive. So what you want to actually have, not to think about, yes, do I need to do my map for this collection first and do my reducer then, or do this reducer first and do my map later on? What you want to do is actually not to think about this. But in scalding, like I said, this line here in the group by, I group my elements, I do sort with take. When I look into sort with take, you see something like this. It's implemented using something called a priority queue monoid. Let's forget the M word for the menu, for now on, just for the moment. Let's focus on the priority queue. Well, a priority queue is a queue with a priority. I'm not going to explain to you some algorithmic stuff. I'm sure you know that. Here, if I have two priority queues, this is what it would look like. I have a first priority queue and a second priority queue. What I can do is actually merge those two priority queues. And what I can have is that I can preserve the order, and my queue is still ordered. It's still a queue with a certain order. I can extract the top K of my priority queue. And what I can also observe is that a priority queue can be empty. Two priority queues can be added in any order. So I have something like associativity, commutativity in my priority queues. Now, you might be wondering, okay, so to do what? Well, this makes me write all this code in one single pass. I'm not having multiple Hadoop jobs. I'm actually doing my left group by the sorter and the filtering to have my top K are done in one single pass because of the priority queue. I'm not doing sort here, append to the filter here, and add something later on. But with my priority queue, I'm doing the merge on the fly, adding elements as they come in. I'm not waiting for something to be blocked and then add later on. Instead, it's working as one single pass of a single job, which makes things like scalding or any other DSL like Scooby that's written on Scala and using monoid very fast, contrary to what you have with things like Pig or Hive that lacks this kind of optimization. They have the data structures, but they don't have this optimization. So now I can do that in a single pass, but what allows me to do that in a single pass is not just because it's a priority queue. It's because that it's associative and commutative. I can add them in any order. I can do the element. I can have an empty priority queue, add elements on any order. I can parallelize all the things. That's something that's very interesting. So I'm like, how can we generalize that? So it's better and faster because it's associative. And associativity allows you parallelism. How? This is something that's associative. You have a simple addition of multiple elements. By doing so, I can have all my elements, do the element in the associate with the addition in parallel for any way I want. And at the end of the day, I'm going to end up with the same result. It doesn't matter which way I started on. Now, once we know that you have something like associativity, having an identity element, the zero, how can you use something like that to actually have a generic way to write big data operation or for analytics? Now, we end up thinking, but do we have data structures that are interestingly associative, have this property of commutativity or having identity? Well, that's where something like abstract algebra comes in. I'm not going to dive into abstract algebra for real because it's something different. I'm not going to do very complicated math this morning, but just to give some definitions. Abstract algebra is a domain of math that's most of the time when I remember first time I studied abstract algebra back in university was like something I never thought I would use anyway. It was so abstract. It was mostly theory. At some point, from my point of view, it lacked really practical uses. But it's really much used in something like compiler theories in cryptography. And in our use case here, which is building analytical systems, what we want to do is actually take just some examples. So we talked about associativity and something called semi-group. A semi-group is actually a set, a number of elements where we have an operation that's associative. A monoid is a semi-group with a zero. A zero is the identity, what you call the neutral element in French. So what a monoid is something that has a zero and is associative. A group is just a monoid with an inverse, and an abelian group is a commutative set where you have a set with an operation that you can have a commutativity. And here, when you have associativity, grouping your element in any order doesn't matter. Commutatives, when you have a commutative operation in an abelian group or a commutative operation in your set, your order of your operation doesn't matter, which makes you write your application actually in parallel. Now, this sounds good. For example, you have a min and a max. I mean, some of you in the room will say, but a min is not a monoid. Yes, a min is not a monoid, nor is a max. A max is actually an ordered semi-group. If I give an order to a semi-group and I bound my set, say for example, I'm starting, instead of going the whole int, I'm gonna take a max starting by 0, and I'm gonna say that 0 if my first element is bounded by here, and my order is the natural order of elements, I can say a max will behave like a monoid, but still not a monoid, but it's associative, and I can say, okay, this identity, every element is larger than this kind of element, then it starts to behave like a monoid. And the same can go with Boolean OR, Boolean AND, the int for addition, the union for set, the harmonic sum, the operation vector, and max, and all the elements. We'll come back, I'll be back here and talk with this in a little more detail. So far, everyone is following me now. It's okay? No one is lost yet, it's okay. That's the most important. Now you're okay. So now I think you like this. Okay, so you have associativity, 0, monoids. Okay, now what? Yes, now let's try something interesting for now. When you work, for example, let's take an example on how we can use this concept into a real analytical problem. Let's say, for example, stream mining. You have a data set in a streaming fashion, and you want to do real-time analytics on that data set. What you want to do most of the time is to actually update your predictions or your dashboard, your counting in real time, every time one observation is made. And you want to do that in a single pass, which means that you don't want to replay your stream once again, because you don't most of the time have the way to go back and replay all your stream. And you don't have unlimited resources for computation. And your memory size is bounded. You don't exactly know, okay, you don't know if I'm going to have something like 10,000 elements coming in per second, or if you're going to have 100,000 elements coming in from second. These are the problems that you have when you want to do real-time analytics on streaming data. This is it's a very problematic way. So when you work with streaming, when you want to build a streaming analytic problem, like everything in computer science, it's about trade-off. You can't have it all anyway. You have speed, you have accuracy, you have space. You need to choose which one to go. And most of the time, what you say, okay, I can replay all my data and have the exact answers, but I'm gonna trade speed with accuracy. I'm gonna trade accuracy for speed. So instead, I'm gonna take all my data on fixed memory, and I'm gonna approximate all my results. Instead of saying that I'm gonna have this exact result, I'm gonna have an error, a probability of mistakes, or a distribution of my error on how my computation is made. So you have many ways to do that today already. You have what you have in descriptive statistics. You have a lot of things to do to deal with streaming data, like reservoir sampling, subsampling, adaptive sliding windows, using time series analysis methods. But that's not, those kind of solutions are not very scalable when you want to deal with very huge, very big data sets, especially when they comes in on the fly. What you want to do actually is to build, you have a special case of approximate algorithms that you can use to do streaming analytics. And most of these algorithms were made actually from the beginning for people who used to work on databases. For example, when you want to do a join in a database, your storing engine, your query engine is actually doing some operation to actually figure out if I want to do a join with this table and this table, is going to scan the larger or smaller table, try to join there. But since you space and time constrained, what you want to do, you do approximation, you make assumptions on which one is larger, which one contains this kind of elements. So they took this same way of thinking to actually take off all these data structures and algorithms and make them work in the real life, not just inside the database. So we have a class of algorithms and data structures for streaming analytics. The simple idea between them is about hashing. In descriptive statistics, what you have, you do sampling, you do reservoir sampling with knoods or all your things, but here what you do is actually using hash. The advantage with hashing is that you're reducing actually not just the space of your, not just reducing the space, because when you hash something like 1 million elements that takes something like 100 gigabytes, you can go back to something that amounts to something like 10 megabytes of data. You're reducing the size of the data set, but at the meantime, you're actually expanding the scope of the scope and the writing space of your data set. One of the most known data structure is actually Bloom filters. Who here knows what a Bloom filter is? What a Bloom filter is? Okay, so basically what a Bloom filter is an approximate data structure that lets you know if an element is not on a set. You have a set of multiple elements. How you build a Bloom filter within that element, and the Bloom filter tells you with exact certitude that an element is not there, but it cannot tell you exactly if an element is there. So it gives you a maybe. When you ask, do you contain this element? It can give you a maybe or an error if something is there. But if the element is not there, it says it can give you an exact answer by saying no, the element isn't there. So the probability of having some false positive is existent. You have a probability for having false positive, but you can't have false negative in a Bloom filter. And the Bloom filter is useful when you're doing join because you want to find out exactly, okay, is this element contained, is this, you have two sets or two tables. What you want to actually join them, you want to find out the elements that are not contained in the other set. So using Bloom filters, instead of scanning the full data, you're scanning the Bloom filters. Because the Bloom filters are tiny, are smaller than actually the huge data set. So you're saving on time and you're saving on space. So why a Bloom filter? This is how it works. So when you want to add an element to a Bloom filter, well, you take a family of hash function, and that hash function, if you find that element, you put a 1 there. So basically you end up having a table of 0 and 1. I'm not going to dive into the internals of all these data structures, just to give you an idea. This is how it works. And when you want to find out if an element is there, you say if all the element, when you do your multiple hashing for your function, it tells you that, okay, if I have 0 all the way, if all my hash function give me 0 for this kind of element, then I'm sure that element is not contained in my data set. If you have something like 1, well, I might have an element, but since I'm working with hashes, I can have collisions. And collisions tells you that, okay, you cannot be sure if it's yours or if it's not yours. Hence, the fact that you can have some errors on this. So this is how it works. And on a higher level, when you actually, yes, it's this is actually the same thing as this and that. So what you need to remember here for the talk is just that when you add an element to a Bloom filter, you're actually using a OR element. If I have B here, if I'm hashing one of my element here is 6, or the element here is 10, at position 10 is 1, 1, 1, 1, well, I'm sure it's 1, the element is there that I'm adding. If I'm trying to find out, when I'm asking the question, do you contain this element, I'm having an AND. If I have a 0, then I'm going to have something that's not there. And 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 OR are monoids. So when I'm doing a query on my Bloom filter, I'm using a Boolean AND. When I'm adding an element, I'm using a Boolean OR, and both are monoids. So if I go back, that my monoid is actually something that's associative, which means that I can run that in parallel. If I have something like 10 billion elements, and that billion elements are indexed in a Bloom filter, instead of asking question to the 10 billion elements, I'm asking instead question to my Bloom filter, which is actually the table of 0 and 1 that you can see down below. Then you're wondering exactly, okay, why do I need to have all my to scan through all the huge data set instead of asking an index table of 0 and 1? I'm saving on time. I'm having something like a complexity of 1, a constant complexity of question, because it's a table. Every question I'm asking there is on O1, and I can use that in parallel as well. So now I'm sure you can see that the Bloom filter is useful like as a data structure, but what makes it even more interesting is that I can have that in parallel when I have a huge data set. I'm doing some MapReduce, I want to do some join, some operation, find out if an element is contained. Well, a Bloom filter is nice in that context. And the same goes for another data structure, which is HyperLog Log. HyperLog Log is actually, I'm not going to dive into it, but instead I'm going to say that it's a sketch that gives you a cardinality estimation. Basically what it says is that if you have a huge data set, you want to find out the exact distinct element, the number of distinct elements that contain in that set, well, you can approximate that with a data structure called HyperLog Log. It gives you what's called a cardinality estimation. So my HyperLog Log size gives you that approximation. And more than giving that approximation, it gives you the distribution of your error. So how can I use that with abstract algebra? Well, the HyperLog Log use something like an harmonic. This is how it works. I go through the slides, and don't know if it's going to be, I'm not going to dive into the crazy math in it. But basically, the HyperLog Log actually has two things. When you're adding an element, it uses a max. Like I said, a max is just behaves like a monoid when you in the context of big data where we are now. But it's, of course, an ordered semigroup. When you're querying, when you're asking a question, okay, what is the size of your data set? It uses something inside called an harmonic sum. And an harmonic sum as well is a monoid. So until now, we've seen Bloom filters. I can find out if an element is in a set, even if I have something like 10 billion elements in my set. That's okay. I can find that in O1 space and in limited amount of time. I can find the size of that element, of the size of that data set as well, using HyperLog Log, and that also is a monoid. I can do that in parallel as well. I can do some MapReduce, some heavy things, or some MapReduce, or actually do that within something that's not MapReduce, but in parallel as well. And that's, I'm already having something like 2 building elements of what you do one way or another within analytics. Another element is the mean hash. A mean hash is another data structure that actually gives you, you can take two streams of data. What you want to do is actually to find out if those streams are similar. You want to find out if one element is containing another element. And the mean hash gives you this probability here, the probability of the intersection under the probability of the union. And that's called a Jacquard similarity. And that gives you something that can give you a similarity between 2 sets. You use that. You tend to do that when you're building recommendation systems. And when you have 2 streams, you want to find out if those 2 streams are similar and if I can discard another one to work on the other one. Well, using a mean hash allows you to do that. You can reduce all your multiple stream of data and find out exactly which ones are similar, so you can reduce your space of working. And a min hash as well behaves like a monoid. Here's another one, which is a count min sketch. A count min sketch is a sketch as well. What it gives is that you have a data set. You want to find out how many times one element is appearing in a data set. You use multiple hash function, and you're using something like a minimum of your hash function, of your elements, and that is a monoid. And at the end of the day, you have a number of occurrences in an element. And if you think about it, the number of occurrences in elements, you can approximate that within a simple sum, actually. When you're doing, in machine learning, when you're doing whatever you do, most of the time are sums. You end up actually doing sums. And here, it gives you the same idea. And since you have min, when you're asking a question, you have a min function, so you can ask into multiple count min sketch and aggregate them. When you're adding an element, it's simple an addition. Both are monoids and both are associative. So you can have a distributed count min sketch of your data. You want to find out the number of times an element is occurring in your data set. You can cut, partition, or shard your data set into multiple sets, ask them in parallel. And the count min sketch will allow you to do that. And this, you can come to another example here, which is anomaly detection. This is what an anomaly detection is like, okay? You have your model. I'm talking about the picture below. You have something like a continuous time series on top. And what you want to do is to find where is the anomaly. So you set up a threshold, and when something goes above that threshold, then you have detect your anomaly. And below, what you're actually doing, this is your algorithms. What you have is actually you have your model, you do some operation on that, and you have an online summarizer. That online summarizer is actually a data structure that actually allows you to find percentiles. You want to find quantiles, for example. You want to find the 99th percentile of your elements. That gives you a threshold you don't want to cross. And to do that in real time when your data is coming in all the time, for example, you want to find which credit card is not very well, is used somewhere it's not supposed to use, where you put in some properties, and at a certain threshold, you can find out, okay, this thing is not okay. And that online summarizer is actually something called, you have many of them, the summarizer. One of the most used is a Q digest. You have a Q tree, and you have a T digest as well. And those are associative intrinsically. So Q3 and Q digest are both a bit alike. You have some differences, and you have a T digest, which is rather new, which is also associative, but it's faster, and you can use them as monoid as well. And what you can do, what you can have with this is that it gives you quantiles, whether you have a continuous data coming in or whether you have already an offline data set. This is okay. This is very neat when you actually, like I said, in fraud detection, when you want to set up alarms, and it's very neat. And those are just some sketches that I talked about. You have many of them. Again, you can build histograms. If you want to do some clustering in real time as well, you can do that in parallel if you use something like ball sketches, which behaves like monoid because they are associative as well. A stochastic gradient descent as well, you can fit machine learning algorithm with that, with a monoid built on top of stochastic gradient descent. So you can see that the thing that's coming here, you can take all the things that you have, take the property of associativity, and actually distribute them on your cluster and actually do some parallel work on them. And this a simple thing what you can have, for example, commutative monoids. You have max, here, HyperLog Log, Bloom filters, like I said. This is just to sum up what I just said before. And all those data structures can be found into a library called Algebird. This library was open sourced by Twitter, and you have all the things that you actually need in it. You have all the HyperLog Log, you have the Bloom filters, the moments, the min hash, the top K as a monoid as well. What you can do is actually plug it into your operation, and it guarantees you through the compiler, through the property of associativity, that your operation can be run into a MapReduce or into another parallel operation. The way it looks like is, for example, you have here, if you do some Scala, this might look familiar. This is a Scala shell, a REPL. You can take a HyperLog Log. This is how you instantiate that. You take a data set. You take a sequence of your HyperLog Log. You want to take a sum, and here you want to find the approximate size. And you call it this way, and at the end of the day, here, it gives you a HyperLog Log. If you want to find all the operation that you want, it gives you an approximation of your size of your data set, and here the operation. So you can find that this is a small data set, so you have 5 and 4. This is the error, and that error is actually, you can bound the error actually. The HyperLog gives you the size, and here you have some example as well with the Bloom filter. You can see that if I have a monoid here, I give my Bloom filter a number of hash, the size of my array, and the seed. I build my Bloom filter monoid here, and I want to find out if it contains the element 1. This is my result, and I can do my operation. And the Bloom filter here, you can find out after most operation here that it contains the operation 1, and here 1 is there. If 1 wasn't there, if you find the example is not well written, but you could find out. I mean, you can find out if your element is not contained or 1 is contained. The same thing goes for Bloom filters, for counting sketch, for decayed value, which is actually find a moving average, for example, for a time series coming in. This is very neat. This is very, if you want to find out, if you want to build your application, this is very important. This is very useful. So to finish, the point here is not to say that monoid solves all the problem. Monoid is just a mean to an end, actually. It's just a guarantee that it provides to you on what you're trying to do. What's important here is that this data structure that you have here, when you're working for huge data sets, you don't want to work on your whole data set. You want to do some operation in a very fast manner. You want to guarantee that your operations are type safe. And in a cost-effective solution, you don't want to add more space to what you have. So using Algebird, where you have these data structures, these approximate data structures, and where you have monoids, it's something that's very useful, especially when you have MapReduce, when you have MapReduce with that in frameworks like Hive or Cascading that actually are written like a succession of multiple steps. But in reality, what you want to do, what you want to have is something that can do the work in one step only. And you can build joins, hash joins by using these monoids, and it gives you guarantee that you can run your operation in parallel. You can find this slide here on my speaker deck page. And if someone says what a monoid is, so don't be scared anymore, okay? You have all the documentation here, and well, this blog is very interesting if you want to get started with monoid and Algebird. So I just wanted to give you some idea of what you can do with this kind of library. So thank you. I'm done. Any
wow.
question?
Wow.
You
Okay,
guys
questions, guys.
Did you go back